Hello and welcome to the Safeshore guide to galvanic corrosion and galvanic isolation in boats and yachts. Let's start with the basics and look at the many different metals used in boat construction. Specifically, we're going to look at just two of these and look a little closer. The two metals we've chosen are the aluminium propeller and the brass skin fitting. Not too interesting at the moment, but let's see what happens when we put them into a saltwater solution. We know from basic electrical theory that metals immersed in salt water carry an electrical charge, and as a quirk of nature these electrical charges are different for each metal. Let's put the theory to the test and drop a couple of probes into the water and we'll check the voltages between the metals. To make life easier, we've attached the multimeter probes to the metals with crocodile clips. We can now clearly see the voltage difference between the metals. The meter reads around 438 millivolts, or approximately half a volt between the two metals. So it's fairly obvious by checking the voltages present between the various types of metals, we can construct a table of voltages present on different metals. Here we have a sample galvanic table showing the voltages present on various metals. Looking at our aluminium propeller, we can expect a voltage of approximately 0.95 of a volt, and on our brass coupling approximately 0.4 of a volt, giving a difference of around half a volt as confirmed by our meter readings. Metals with high voltage readings we class as anodic, and with low readings we class cathodic. It's worth noting at this stage metals such as aluminium, zinc and magnesium sit at the anode end of the scale and carry the highest natural voltages. Brass, stainless steel, copper and chrome sit at the cathode end of the scale and naturally have lower voltages. Let's go back to the tank and see what's happening. We now know we have the propeller, the most anodic metal in the tank, with a natural voltage of approximately 0.95 of a volt, and the brass being the cathode with about 0.4 of a volt. The two metals are separated by an electrolyte. In this case, it's the salt water. Because the metals have no physical connection, no current flows between them, and the metals remain stable. We've now connected the two metals together. As the different voltages attempt to equalize, a current begins to flow through the water, generated by an electrochemical reaction between the metals. Over time, the most anodic metal begins to deteriorate. In this case, it's the propeller. To minimise corrosion in metal hulls, we attach multiple anodes directly to the hull. In non-metal hulls, we electrically bond together the hardware, and using the central bonding point, we add the anode to the circuit. In either case, the anode eventually sacrifices itself, protecting the other metals. When the anode is gone, the next most anodic metal will corrode. So let's have a quick look at a variety of anodes, all carefully selected and positioned to protect our valuable hardware. Here we have a selection of new anodes, ready to go back in the water and protect our underwater fittings. Eventually the anodes will of course wear down, at which point the next available metal corrodes. Regular inspection and replacement of worn anodes is obviously essential. Let's move our boat into the marina. A big advantage when we can utilise shore power electricity and stay warm all year round. We connect our power cord into the shore power supply, and our next door neighbour does the same. The shore power lead contains 3 cables, a live, a neutral and an earth or ground wire. Our next door neighbour has the same. Let's see where the ground wire goes. It arrives from boat number 1 on the right hand side. The green wire then connects to a metal grounding plate in the power box, travels via the metal ground plate to connect to boat number 2 on the left hand side. In the marina, boats are now interconnected via the green earth cable. This now creates an easy path for galvanic currents to flow between the boats, increasing the risk of corrosion. If the boat next door failed to fit anodes, he won't worry, he has a perfect path to yours. Obviously we need to break the connection between the boats, but we cannot simply cut the green wire. This is essential for our safety. We need a device that will isolate the boats from each other, but at the same time allow any fault current to pass safely to earth. So here's the solution. We install a galvanic isolator on board the boat and insert it between the shore power inlet of the boat and the mains consumer unit on board. Here's a quick diagram to show installation. We simply break the earth cable and install the isolator between the 2 wires. So how does it work? The galvanic isolator is a device which ensures all safety circuits operate as normal, but at the same time blocks any potential galvanic problems between the boats. All on-board fuses, RCDs and other safety devices operate as normal.